So we'll start the session at 6:10 or something. Let others join.
Its quality of audience has come down
Yeah.
all everywhere, particularly in civil engineering.
Hmm.
You know, I have passion for teaching. While
Okay.
working in Central PWD also, all over the country I've been teaching. School of Planning and Architecture, Delhi, then NIT Jalandhar, then DAV Institute at Jalandhar, Port Blair also I taught. And geotech is common to me. Other subjects have been changing.
Okay.
Uh, I like this subject, even if my master's is in now consultancy also I'm doing in geotech only. I like this subject
Okay.
somehow,
Hmm.
and I got first prize in this subject in Delhi University.
Oh, nice.
I this Punmia book was available at that time also. First edition was
Uh-huh.
Alam Singh and Punmia. Then they separated out. Dr.
Okay.
Alam Singh wrote separate books on instrumentation and testing, and Punmia had written that book also. So Dr. Alam Singh allowed him to write separately. That is how this BC Punmia editions started after that. The
Oh.
story was told to me by the publisher.
Oh.
Delhi on one side used to be my college, Vajrani and Ratwani. Vajrani used to be my teacher. Across a bridge, it was all publishers on Nai Sadak. So I know all these publishers personally. We used to go there, say hello, discuss. So publisher told me that there was some difference between Dr. Alam Singh and Punmia. Alam Singh is writing separately, so he has allowed Punmia to publish in his own name. So the book which we read, that was authored by Alam Singh and Punmia both.
Okay.
Dr. Alam Singh was a professor at MBA Engineering College, had and not married. I saw him at Roorkee in 76, 77, International Symposium on Soil Structure Interaction. Only once I met him. Punmia, by chance, I have not met.
Oh, okay.
But his books are very popular.
Yeah, yeah, it's popular. I also read that during my BTech.
I had studied this subject even before it was taught in the class.
Oh, okay.
And in my fourth year, we used to have 5-year course. 80-90% of the time I was devoting only to this subject. And first prize. Only three students passed, all others failed. They had to be given grace marks. I got the highest score. Very typical questions. They are giving liquid limit that is related to CC, compression index. From that, they are asking you to find out the value of consolidation. So unless you know all those relationships, you cannot solve. All the questions were like that. I could solve 10%. When they are asking earth pressure, they told us to solve using Coulomb's theory. Coulomb theory, expression is complicated,
Yeah.
difficult to remember. But if you know that Revan's diagram is based on that, no. In Dr. Abhishek's session also, very few.
Yeah, so it's 6:10. I think I should start.
Yeah.
Okay. So I hope you can see my screen.
Yes.
Okay. Uh, Good evening, everyone. So today we are going to have a discussion on the subsurface exploration importance and techniques involved, the week 6 lectures. Uh, I am Balram Shah. I am a PhD scholar at ICVAR at ISC Bangalore, and I am the PMRF for this subject called subsurface exploration importance and techniques involved. So today we will be discussing about the week 6 lectures and some of the assignment questions and some of the things. So let's move on. Coming to the first question, that is, which of the following plate boundaries generates new land masses? So in the previous week also we have done this, I guess, about the convergent plate boundary, how the new land masses comes up and how the land masses get consumed. So for first case, what is the question? Which of the following plate boundaries generates new land masses? So your options are divergent plate boundary, convergent plate boundary, transform plate boundary, and none of the above. What will be the answer?
I think should be convergent plate boundaries.
Okay, wait.
Divergent, sir.
Okay, let me stop it here. I will share screen. This. Okay. Uh, so in the last class we have discussed about the divergent plate boundary and the convergent plate boundary. As you might remember, divergent plate boundary means the plate boundary will be moving in this direction, isn't it? So what will happen? The materials will come upsides, and so what will happen? The materials will get deposited and it will cool down, and then new land masses will be created. If convergent plate boundary is there, let us say this one is the convergent plate boundary, then what will happen? It is moving in the direction uh, towards each other, so this gap will be filled. And what will happen if, let us say, some materials was there, some kind of small hills or something, because of this it might get into this. So what will happen in the case of convergent? So this one is the convergent plate boundary, and this one is the divergent plate boundary. So in which case we are seeing that new land masses are generated
Divergent.
in the divergent plate
Divergent.
boundary. So the correct answer will be the divergent plate boundary. Okay. Okay. So look at this. Okay. Now I will go into this first. Okay, so as we have seen, the answer for this was divergent plate boundary. Okay. Now coming to the week 6 lectures, as you might have gone through the lectures, this in this week we are going to discuss about the offshore environment, how we are going for offshore exploration or offshore subsurface exploration. But let me say that this offshore subsurface, anyway, we offshore exploration we are going in the last module of the lectures. But in this lectures, what we are doing, we are very in a very short period of time we are covering the offshore exploration or offshore environment. The offshore structure is on its own is a very vast topic. So in some institutes in India also, the offshore structure has been one different stream for the studying. Okay, okay. Let's move on to our what we are studying. In this slide that you can see, what is happening? Anyone?
This is
Continental drift, sir.
continental drift.
Yeah. So it's called continental drift theory. So in this, what is happening, that let us say very long back in around 1900 or 1912, based on this theory of continental drift, by collecting all the evidences that the entire earth was a single landmass, and it got broken down like what you are seeing in the slides. So the all the earth, when it was one landmass, it was called as Pangea, and which means all earth in German. And then it has been broken down, as you can see, and then it was broken down in Laurasia and Gondwana land, and simply it has gone broken down for about several million years ago. Okay, so present configuration that you see in the world map or whatever config UTM that maps and all, and that is the result of continuous process of this breaking of this land masses. So referring to the continental drift theory, this rocky crustal medium will is floating under the over the mantle. Okay, now this at continents the thickness of crust is in order of 80 to 90. Okay, I will write it here. So continent continental drift theory we have discussed. So at continents, what happened? At continents, the thickness of the crust is around 80 to 90 kilometer. Thickness of crust is around 80 to 90 kilometer. Whereas in ocean, if we see, the average crustal thickness is around 10 kilometer. Okay, so as we have seen, if there is divergent plate boundary somewhere, what happens? New land masses are getting generated. But whenever we have the convergent plate boundary, what happens? The land mass get consumed, and sometimes it also happens that there is no creation or the land consumption. When does this happen? When we have this transform plate boundary, so there will be relative motion, but there will be no consumption of the landmass or no generation of the new land masses. So that is called as transform plate boundary. uh, so now coming to the ocean and this continent boundary. See in the figure you can see. Okay, okay. So here what we can see is this is the ocean or continent boundary. This part that you can see in the left or the extreme right, this starts the continent, and in between we are considering that this is a ocean. This is a very vast ocean. Just to visualize, we have one kind of picture here. Okay, so this one is the continent landmass and this one is the ocean. So now what we'll understand that how the topography inside the ocean or near to the, as we are going to discuss about the offshore structures or offshore exploration, the ocean or continent boundary, there we will be considering about the offshore structures or the offshore exploration, and hence we'll be discussing about that first. So here you can see in okay, I will start from the left. So now you can see here this continent is starting, and after that the the point or the plane which is submerged in the sea, it is called as continental shelf. Okay, now if we move towards more right, what we can see, the shelf or the land mass is getting gradually slopey, having some slope. So now when it was kind of plain or the slope was very little, that time the place is called as continental shelf. But when the slope is getting having very fast slope with very less distance, what we can see, that is called as continental slope. Okay, Now when this continental slope will end, and it will go to the abyssal plain. This one, the plane that you can see, is called as abyssal plain. Now the point or the line where whichever will be there between the continental slope and abyssal plain, that is called as continental rise. Now again in continental rise, we will have the this upper rise and lower rise that we'll be seeing again. Now in between the ocean also, we can have different land masses or different topography. As you can see, the ocean bed that we can see is not only a flat plain, but it can have some sea mounts, some volcanic island in between. There can be mid-ocean ridges like this one is called ridges, or there can be trenches. Okay, so now we'll be seeing, as we are going to discuss about the offshore part only, so we'll be just focusing about that. So we'll be moving into the next slide. Here we can see this one, as you can see, was the continent in the previous figure. This one is the continent, so we'll be discussing about this. Okay, now see what we can see. This is the coast. Now after the coast, when some part of the plane is submerged with the sea, that is called what? Continental shelf. Okay, and after continental shelf, when the slope will be increasing, that will be called as continental slope. After the continental shelf, what will be starting? It will be continental slope if there will be very vast change in the slope. And when the continental slope is going to meet the abyssal plane, that is called as continental rise. Again, this continental rise, based on the slope, it will be called as upper rise and lower rise, or upper rise and lower rise. And whatever crust is there beneath the continent is called as continental crust, and whatever crust is there between the below the ocean is called as oceanic crust. And below this, the red that you can see is the mantle. Okay, now okay, and the total of this continental shelf, the starting point of the sea uh, till the starting point of the abyssal plain, that is the continental rise, will be called as continental margin. And this is the total deep ocean basin. There can be some ridges in between, there can be some trenches, as we can see in this figure also. We have seen there can be trenches, there can be mid ocean ridge and all. So like this, the topography or the physiography of the whole ocean is there. So what all we have seen. Okay, okay. Hmm. Okay, so what all we have seen, I'm not going to draw because I have given a good figure in that. So what all we have seen, we have seen continental shelf, we have seen the continental slope, and this continental shelf plus continental slope is called what? It has some name. What was that?
Continental margin.
Correct. So it was called as continental margin. Okay, then we had, so what is continental shelf? It is the, okay, let me write it here. It is the submerged portion of the adjacent landmass. Okay. And continental slope anyway we have discussed. So after that it starts, and the continental slope is ending, and then the abyssal plain is starting. This line is called the continental ridge line, or that point, if you consider, that is called the continental ridge or the shelf break. Continental ridge or the shelf break. Okay, and then we had the abyssal plain, and then we have discussed there can be not only the flat plane in the ocean bed, but it can be having some other topography kind of The sea mounts can be there, volcanic islands can be there, then trenches can be there, mid ocean ridges can be there, and all. So the now this continental margin is very important, because that is only what we are going to discuss right now in this all the lectures, upcoming lectures, and whatever lectures we have seen, because there only we are going to construct our offshore structures. So this continental margin, what we have studied, is extremely important, and like most promising location for like why we are only more focused on this continental margin, because in that area we'll find or have the oil, mineral, gas exploration and all. So because of that, this continental margin is important. And what we have seen that, sorry, that more than 20% of the total ocean floor is having the continental margin. Okay, so the physiography of the ocean bed is clear. Am I clear with all this? Then we'll move to the questions. Next questions, I mean. Okay, so we'll move to the next questions. Okay, moving on to the next questions. So the question is, continental margin consists of, just now we have discussed.
C.
Yeah, C, correct. So what is this? So the correct answer for the continental margin will be the continental shelf and continental slopes. So answer will be C. Okay. Now next question is, continental margin covers more than dash percent of the total sea floor. Just now we have seen that the
20%.
yeah,
Yeah.
more than 20% of the total ocean floor, or the or we can say the sea floor, this continental margin covers. Okay, it is around some it's much higher, it's near to 74 into 10 to the power 6 kilometer square of surface area for the continental margin. Okay, so next question is, the average crustal thickness at continents and ocean ranges are between dash and dash respectively.
D. D will be the correct answer.
Yeah, so as I have discussed just now, that 80 to 90 kilometer will be our crustal thickness at continents, and around 10 kilometer it will be at the oceans. So the correct answer will be D. Okay, moving on to the next question. Source of poisonous gases in offshore environment are called as, okay, this I have not come till now. Okay, let me see, maybe, okay, this will be after this. Okay, as we have completed this, what is the physiography and all, so now we'll come to offshore. This question I will come later. So coming to the offshore structures, what is offshore structures? Offshore structures is any kind of structures or any kind of construction, or offshore construction is the installation of structures and facilities in a marine environment, usually for the production and transmission of electricity, oil, gas, and some other resources. So offshore structures are the basically are the structures that we are doing in the marine environment, or in the sea floor, or kind of near the ocean. Now this, if we divide this offshore structures broadly, if you divide the offshore structures, will broadly be divided into floating type and fixed platform type. Okay, here you can see in this figure, change this pointer, there are some of the platforms that you can see here, isn't it? So there, that can be anchored and all. and this is one kind of offshore structure having the vessel here. Then this kind of wind turbines will be installed near the sea. So these are some kind of offshore structures. So where mainly we see this offshore structures to have the oil and gas exploration, mineral exploration, then even as, let us say, even as support against the lateral movement for transmission and communication cables across sea floor. Okay, let me write it down. Okay, so what I was discussing about the offshore structure. So what I said, okay, let me write it first. Offshore structures. So it's the, or as I said, offshore construction is the installation of structures and facilities in a marine environment. So mostly it is for oil, mineral or gas exploration. So even as support against the lateral and movement for transmission and communication cables spread across the sea floor, we go for this offshore structures. As we have seen in the figure, for wind turbine was also there. So firstly, lateral movement for transmission and communication cable, transmission and communication cables that are spread across the sea floor. Then we have the wind turbines or the wind. As we know, wind is a source of green energy. So in comparison to landmass, in landmass, if we anywhere we as we are constructing more and more and more, the landmass over the continents are gradually decreasing. Anyway, so in comparison to landmass, sea levels are better level, resulting in the continuous flow of wind throughout. Okay, so that's why we go for the wind turbines or wind energies near the oceans or the near at the offshores. So wind turbines, if it is erected in the sea, it can be more efficient sources of energy, because there will be more better level, resulting in the continuous flow of wind throughout the offshore. So that's why we go for the wind energy or the wind turbines near the or at the offshores. Then there are several other applications why we go for offshores. Artificial land, if you see the artificial land, like I said there, uh, and this in the Dubai there is Palm Island. You must have seen that very nice island. So that kind of artificial islands. Then support ports can be there, because the main ports that will be there, they can be accessible every time. So sometimes what happen, the ships will be coming to the supported ports, and then it will be moving towards the main ports. So supported ports, then airports, then bridges, tunnels. In India also, if you see, we have the that Bandra only in ceilings in Mumbai, that bridge. So that kind of several offshore structures will be there. And this sea floor is feasible for long-term storage of carbon dioxide. If you go for ocean alone is a very good sink of the carbon dioxide gas. Around 25 to 30% of the total carbon dioxide in the atmosphere is being taken by the ocean, and around 50% of the oxygen in the atmosphere is given by the ocean. So okay, we should not go into that. Anyway, just to have the information, I told that ocean is a very good sink of the carbon dioxide. Similarly, the sea floor is also feasible for long term storage of the carbon dioxide. Okay, So how this offshore structures and the onshore, because previously whatever we have studied in this in that we have studied about the subsurface exploration of the onshore, okay, where these ocean seas and all were not there. So how, why we are going for offshore structures first, second how it is different from the onshore structures. Any answers?
In offshore structures, we have more of turbulence, uh, lateral dynamic loads, etc.
In offshore, yeah.
Generally, which are predominant.
Yeah, correct. So first one, as he said, that there will be higher lateral loads. Lateral loads in the sense what? Lateral loads can be winds, then water currents, and so on. So in the on offshore, if you see, there can be higher significance or significantly very higher lateral loads like winds, water currents, and all. But in offshore, we don't have this much of higher lateral loads. There will be some wind, seismic activities can also be there, but not this much amount. Okay. Other than that, the area, if you see, it will also be significantly larger for offshore than that of the onshore structure. Then different types of client will be involved, or the government authority, because there can be some ecological perspective and all that will be coming. Okay, then we have different client and government or governing authority, if I say governing authority. Then the design life of the structures that we are doing for offshore, how much is the design life, like approx, if we say, for offshore structures?
Maybe maximum 30 years or so.
Yeah, around 25 to 50 years minimum, maximum, if we see. Then in the onshore, what we do, we directly do the structure there. But in many a cases, what we do in the offshore, we construct all the structures, most of the structures on the onshore, and then we take that and assemble at the offshore. So we construct it at onshore and then assemble it at offshore, whatever structure is there. Okay. Then let us say if we want to improve the ground, you can do that, but it's very expensive. Mostly the location that will be taken will mostly be good, having good strength characteristics of the ocean bed or soil layers which is beneath the ocean bed. Then these offshore structures, mostly it is exposed to good number of geohazards. What is geohazards again? Like the hazards, or like whatever hazards are there which are responsible for loss of life, and then finance in related to the geological, the geotechnical characteristics as available, or in the, like, in that structure wherever we are going to build the structure. If because of that, because of the construction or because of the destroy, if the structure is getting destroyed, then the hazards which are responsible for the loss of time, loss of finance that are associated with this, whatever geology is there, whatever geotechnical features are there in that structural area, or anyway any near area or the vicinity of the proposed offshore structure, those type of hazards are called geohazards. So in the case of offshore structures, it is exposed to large number of geohazards like tsunami. Okay, I will write like tsunami. Then if you go near the ice shelf and all, there it can be impacts through ice, then several other. But again, one important aspect is the ecological consideration. because as we know, then in ocean we have other kind of life. We have flora, fauna, and all. So we have ecological considerations there, right? And then again, there can be several cyclic loading in the offshore structures, or in the offshore. If you see, mostly the loading that you might get will be cyclic loading. What is cyclic loading? Anyone? Examples, some examples of cyclic loading.
Wave motion.
Okay, wave motion. But I'm asking about the loading for this structure.
Certainly, repeatedly the same load is coming.
Yeah, that is
Say,
called cyclic loading.
yeah,
If we are
uh,
having the same loading again and again, that is called cyclic
yeah.
loading. So some examples can be a crane which is repeatedly lifting weights. That can be one kind of cyclic loading. Then there can be some ship or vessel which is exposed to the winds and waves, etc. All this will be coming under cyclic loading. So in most of the cases in offshore structures, the cyclic loading will be the most dominating parameter. Okay, so this kind of several other factors will be there for the offshores. Okay, so let's move on to the questions. Okay, so before this there was a okay. I talked about the geohazards also, right? So if we don't plan the or if we don't predict the future scenarios of the structures that we are building, if you're not having proper design, if we are not having proper design, or let us say proper construction, then what can happen? The damage to the offshore structures can happen, and it can lead to several constraints. Okay, it can have the geo hazards, then it can lead to ecological problems, and it can lead to financial loss, it can lead to several other losses. So the predicting the future for the structures is very essential to prevent the damages to the offshore structures. Okay, so before that, uh, oh sorry guess I have not came across till now. Okay, so I'll come to that question later. Now coming to the next question. So the next question is, which of the following is not true for the offshore structures? Your options are: offshore structures are built for oil and gas exploration, offshore structures are significantly larger than onshore structures, then offshore structures are exposed to small lateral loads than onshore structures, or none of the above.
C. C appears to be correct.
Yeah, correct. So the answer for this will be anyway, because the question is, it is not true for offshore structure. As we have seen, offshore structures are for mainly for oil and gas exploration, and it needs sufficiently larger area than the onshore structure, but it has high lateral loads also, or significant number of a significant amount of lateral loads than that of the onshore structure. So the correct answer for this will be the C. That is, offshore structures are exposed to small lateral loads than onshore structures. That is not correct. So it needs larger. Okay, next question is, which of the following location in the ocean is most suitable for oil and gas exploration? This I have discussed when I was
C.
explaining the
C.
feasibility.
Continental margin.
Okay, Gopal, any answer? Yeah, so what we are seeing, the location in which the oil and gas exploration is most suitable is the continental margin. What was continental margin? The total continental shelf plus the continental slope. So there it is most suitable. So correct answer will be the continental margin, C. Okay, next is, dash are transported from the landmass by various weathering agents. Okay, so before this I will explain something. Okay, so as I discussed, and this cycling loading, as you have seen, this cycling loading is around 10 to the power 8 power of lateral cyclic loading of various amplitude will be there in the offshore structures. Anyway, what I was there. Okay, geohazards, as I have seen, what are the hazards that will be responsible for the loss of life and finance, that will be called as geohazards. Okay, now coming to the sea floor consideration, and before this, as we have seen, the ecological consideration is also very important. Okay, so sea floor considerations, because most of the thing we'll be doing at the sea floor only. So though the as we have seen in the physiography, that though the sea floor at majority of the locations are flat, but there will be the variations in soil characteristic available at the sea floor, isn't it? So in as we have seen in the physiography, there will be presence of faults, those faults while exploring the larger area, if you do, particularly along the alignment of the oil or gas pipeline. Like if you are going for the oil or gas pipeline, you will be going for several kilometers, so you have to do the exploration for the larger area, and you have to check if there is any kind of faults present in the distance or whatever portion that you are going to construct. So you have to go for that. Then any movement along the fault is there. If there is any movement along the fault, what can happen? Let us say you have the oil and gas pipeline, and if there is any elevation change, then what will happen? It can lead to the failure to the pipeline. Then other than that, why the seafloor is important? The chemical characteristics of the water that is available near the seafloor, it will affect the strength characteristic of the soil. Then also, what is the effect of the construction material? Then flora and fauna, as I have discussed, that ecological consideration is the must for any kind of offshore structures. So flora and fauna at the near proposed site, whatever existing, and after the project is completed, then we have to we have to keep in mind, or we have to be there, that the ecology that was there before the construction should be like it should not be changing that much. The change should be minimal, or there should be no changes in the ecology. But for construction there will be some kind of changes, but what we'll be doing, we'll be considering that okay, minimal number of or minimal amount of this change will be there in the ecology. Okay, so what all we have seen, that gas pipelines, then water characteristics or the chemical characteristics and all. Okay, but again, what can happen when we are going for sediments? Okay, there can be unconsolidated sediments that is deposited in the very recent time. uh, so if the settlements or if the sediments which has been unconsolidated, this means that it is very recently sediment has happened. So what happened if we construct any structure there? Did you get my question? What I asked was, let us say,
Shear stress will be low, sir.
what?
Shear stress will be low.
Yeah, shear stress will be low. This means what? That if the sediments are very recent times and we are doing construction there, So what will happen? Even the primary consolidation has not been done. So what will happen? The nature of
Yes,
the
settlement will happen.
yeah. So
Settlement will happen, sir.
yeah. So it will be softer in medium, and hence it will have less strength in it. So that's why it can lead to failure. Now coming to the this, if let us say a soft medium when it is dissolving with the seawater, or let us say whenever the organisms in the ocean or the sea dies, what will happen? It will mix with the water, and that can form calcium carbonate as the precipitate, and the calcium carbonate, when it will be mixing with the water, it will form the calcite, and this calcite will hold the soil together. So its holding capacity, or its binding characteristics, may vary considerably based on what type of medium is there, and how it is reacting with the water. Okay, so the calcites, then consolidated sediments, and so on. Okay, and again in the pore fluids of the subsurface layer within the soils, what can happen? There can be small bubbles, and in that small bubbles there can be gases present, and mostly those gases will be the layers of nitrate gas. But and when we are going for the subsurface exploration, let us say geotechnical investigation we are doing, let us say we are doing drilling. So in case the drilling assembly is penetrating through the such deposits, what can happen? This can lead to explosion, or explosion in the driving assembly. Because what is happening, you are doing the drilling, and there are several gases that are there in the pore fluid as the bubbles, and when it will interact with it, explosion will happen. So further, when explosion will happen, the gases will be coming out, and those gases are highly poisonous, and it can even lead to death. And that those locations at which this gas deposits are located are called sour gas fields. Okay, now so what we have to do, either such location should be avoided, and if it can't be avoided, we have to have proper planning or proper preparedness to avoid such kind of accident. Okay, other than this, there can be sand dunes that are available at the sea floor, because sand dunes also, because of weathering or because of the wind, it will have the continuous process of movement due to deposition on one side and soil erosion on the other side. So this presence of sand dunes can bury the structure and can compromise its surfaceability, because if much sand dunes are coming, what will happen? The offshore structure will get like covered with the sand dunes, so it can compromise its serviceability. The design life that we have considered will get reduced, so that should also be kept in mind. Okay, other than that, present of hard seabed will offer higher resistance against the pile driving if required for the project. As we have seen in the subsurface exploration before, in the lectures in the onshore, we go for all the preliminary survey or preliminary investigation, then we go for detailed investigation. Such kind of investigation will go in offshore structures, but more kind of investigation we have to do, because here we are having very expensive thing. If the structure is getting destroyed or demolished, it will have a huge financial loss, it will have huge ecological loss, it will have several other losses or damages. That's why we have to go, whatever investigations we are doing, it should be on the top notch. Okay, okay, so coming to the questions. Okay, now we can start that question. Okay, so next question is, Sources of poisonous gases in the offshore environment are called as calcite deposits, sour gas fields, gas dunes, or gas deposits.
So gas
B.
fields.
Yeah, correct. So the correct answer will be the sour gas fields. That is B. Okay, this all we have seen. This all we have covered. Yeah, this also we have done. So next question is, DAS are transported from land mass by various weathering agencies. Now, when we are discussing about seafloor, okay, this I have not discussed. Okay, so this seafloor, we have to go for detailed investigation, as I said. Now we can know the what are the sediments that are there from the. There are different maps or different agencies which will give you map, like let us say for environmental ecological consideration that I said, there are several agencies like Bureau of Society and Environmental Enforcement. It will give you what to say, how what all ecological considerations should be considered, like that. For let us say sediment thickness you want to know, so like that there are several USGS, some National Geophysical Data Center is there. They also give you the thickness of sediments across the globe. Then this as anyway we know that sediment thickness is more near the continents while it is minimal in the ridges. In the figure you must have seen the mid ocean ridges, so there it will be minimal the sediment thickness. Now locations where there is no sediments or very low sediment also exists, particularly because these are washed away by the strong water currents. Okay, though the land mass is only 20% of the oceanic area, but 75% of the sediments will be whatever are available are of marine origin. Now the sediments that you see on the sea floor are coming from two sources. Okay, uh, okay, let me not write. So those are firstly from the land mass, as I said, because land mass is only 20% of the oceanic area, whereas the 75% of the sediments are available from the marine origin. So mainly there will be two sources for the sediments that are available. First one will be from land mass and second one will be from marine origin. So okay, should I write it here? Yeah, can you see that? No. You can see. Okay, where's my pen? So there are two types of sediments available, as I said. Sediments available based on where are the sources. The sources can be the landmass or it can be the marine origin. So the first one is the terrigenous sediments that are available, that is called terrigenous sediments. So the sediments which are transported from the landmass by various weathering agencies such as rivers, glaciers, wind, gravity, all this. If because of all this agencies, there are weatherings happening, and from the landmass, the sediments are transporting towards the sea floor, and the sediments are getting deposited. Those kind of sediments are called as terrigenous sediments. And second one is pelagic sediments. What are pelagic sediments? As we have seen, there are two sources, that are landmass and marine origins. From landmass, whatever from the weathering agencies it is coming, it is called terrigenous. So the sediments which are settled at the seabed through the water column that is there, from the sediments which are getting settled from there and are of marine origin, those are called as pelagic sediments. Okay. Okay, so I will stop this here. So the question is, DAS are transported from landmass by various weathering agencies. What will be that? Just now we have seen. What kind of sediments?
Terrigenous.
Yeah, correct. So correct answer will be B, that is terraceous sediments. Okay, and the next question is, okay, dash are settled at the seabed through the water column and are of marine origin. Anyway, the terraceous sediment from landmass, and if it is of marine origin, it will be pelagic sediments.
A, A.
Yeah, correct. A. Okay. So before this, now we'll be coming why we are doing this site investigation in offshores. What are the main objectives of having offshore structures? Presenting. Share screen. Start. So what are the main objectives of the offshore site investigation? Objectives of offshore site investigation. So what are the main objectives of offshore site investigation?
Oil and gas exploration.
Sorry, oil and
Oil
gas
and gas
exploration.
exploration.
Okay, okay. Anything other than that? Several things I said. One is to have the exploration.
Artificial islands.
Yeah, yeah. But
Artificial islands.
those are the
Bridges.
whole exploration thing. I'm only talking about the site investigation. Okay, so mostly for selecting the foundation. So we have to design the foundation. So what type of foundation should be there? What are the designs for the foundation? Then how it is getting constructed or execution is done. That is the laying of the construction or the laying of the foundation. That should be uh, like, if we have completed the site investigation, so what it will do, it will give sufficient information about what type of foundation we need to construct at the location. Then what design should be there, what kind of execution should be there, like what how it should be laid. So the offshore investigation will give you or will provide you sufficient information about this. Okay, then and this information where we'll use the offshore site investigation, or let us say the information, if I say, so why we need this information, that is what my question is. Okay, so firstly is selecting the foundation, and other than that, for any other design, as you have seen in the figure, the offshore structures slide that I was showing, there were several anchors that can be there in some kind of structures. So to design the anchored system, if there is any for such some kind of construction, then to get the design of the anchored system also, we need this offshore site investigation information. Then let us say there are some lateral loadings, or let us say some lateral events, if you say, not kind of lateral event, kind of horizontal loading. Okay, loading only I would say. Lateral loading, kind of, let us say if there is some seismic activity, so if we have the information, like geological information of the site, we have completed the detailed investigation, we have all the information about what kind of geology is there, what kind of strength characteristic of the soil is there, then we can go for like what kind of if some magnitude of seismic activity is there, then how to be prepared. Okay, what all possible connections we can design. Okay, that kind of thing. So for designing the connections for that, then to quantify possible cyclic loading, like how much cyclic loading can be there for that structure, possible cyclic loadings then to understand the ecosystem, because as we know, if something is happening, much thing is happening to ecosystem, that construction will be stopped. Okay, because there are several regulatory agencies, as I said, Bureau of Environmental Enforcement is there, Bureau of Society and Environmental Enforcement is there. So there are several regulatory agencies are there which will ensure that the flora and fauna of the site and its vicinity should be brought back to its original condition, or the changes that is happening should be very minimal after the end of the required construction. So to ensure this, the environmental survey must be performed. Okay, so and other than this, why we need this information of the site investigation? Let us say we are trying to change the design parameters of the structure during the construction. That is almost like impossible, because if we are changing the design parameter, everything for the construction will change. So for that kind of thing, for ground improvement, what we have to do, we have to have proper site investigation, so we can do the preparedness to handle any kind of accident that is happening during any phase of construction. Okay, then to explore what kind of suitable construction materials is required, and then to understand what kind of geohazard can be possible at the site of interest. So these kind of this kind of uh, help we can get from the site investigation. If we are doing the offshore site investigation, like total detailed site investigation, firstly anyway we have to go for preliminary survey, then we are doing the detailed investigation. Based on all this, we can based on the investigation that we are doing, we can get help for each of the points that I have mentioned. Okay, now uh, as I said, there can be several agencies which are providing you the thickness of the sediments, then geological maps, the datum of the chart, sorry, the chart of the datum, etc. All these things will also be available for your investigation. Okay, so mainly um, um, very fewer times we are going for geotechnical investigation, the drilling and all. We go for that for some kind of structure, but we can go for geophysical investigation, as we have discussed, because the geophysical investigation is kind of non-destructive uh, uh, cons- non-destructive survey, you can say, or non-destructive test, you can say. So mostly we go for the geophysical survey, or the non-destructive test. As we have studied seismic reflection survey, reflection survey, and all, we can go. But mostly for this um, in the offshore structure, mostly what we need first is what is the water depth, then what kind of layer is there on the ocean bed or the seabed, then what are the subsurface layers, or the layers that are present below the ocean bed or the seabed. So mainly these three things we have to see. So to know the, or to measure the water depth, we go for bathymetry. Okay, or bathymetry mapping using the echo sounding, then swathe bathymetry. There are several other methods. So what I said, mainly we have to understand what is the water depth, what are the materials that are present in the water depth, that also we have to go for. Then what kind of sea floor is there, okay, or what kind of obstacles are there. So to understand these obstacles or whatever sea floor is there, we go for sonar. That is okay, on that I will come in. And then to understand the stratification, or the layers that are present below the seabed. So for that we go for seismic reflection survey and all. So as I said, what I said, the sorry, geophysical survey. So mostly what we need, water depth, or whatever in water, what kind of things are present, then sea floor, what kind of sea floor is there, then thirdly the stratification or the layers, stratification or the layers. So mostly for the for knowing the water depth, we go for bathymetry. Now what is bathymetry? And mainly this bathymetry, what why we do, to know the water depth, to have the 3D imaging of the seabed, Okay, I have one video for the bathymetry. Okay, first I will show you that. So what is bathymetry and why we go for bathymetry, that I will show you. Okay, I will show you one video. Okay, wait. Can you see the screen?
Yes, please.
Okay.
What is bathymetry?
And can you hear the sound of the video? Like when it
Yes,
started?
yes.
You can. Okay.
Bathymetry is the science of measuring the depth of water in ocean, riverine, or lake environments. What kind of information can you get from bathymetry? Just like the surface of the land isn't always completely flat, the surface of the seafloor is full of various features like reefs, ripples, mountainous ridges, deep canyons, and even shipwrecks. The bottom of the ocean is also very dynamic, meaning it's constantly changing. Bathymetry data provides scientists not only with a depth measurement, but also a picture of what the seafloor looks like. This can provide information about current and past conditions, what kind of substrate or the material that exists, and if there are any hazards for vessel navigation, among other things. How do you collect bathymetry data? Measuring water depth is not a new concept, but the way we do it has evolved over time. Historically, scientists would lower a lead weight attached to a rope over the side of a vessel to record the depth of water. Today, we use active sonar or sound navigation and ranging. A transducer emits a pulse of sound into the water column, which then bounces off the seafloor and then returns to the transducer, just like an echo. The time it takes for the sound to travel through the water column is recorded and then calculated to provide a depth measurement. Scientists at the U.S. Geological Survey St. Petersburg Coastal and Marine Science Center primarily use two types of sonar transducers: single beam echo sounders and multi-beam echo sounders. A single beam transducer repeatedly emits a single pulse of sound directly beneath the vessel, providing a single depth measurement along the traveled track line. A multi-beam transducer repeatedly emits hundreds of pulses of sound in a fan-like fashion beneath the vessel, providing a large swath of depth measurements perpendicular to the vessel's track. How do you analyze or interpret what bathymetry data means? After the survey vessels return to the dock, the data acquired is imported into a suite of special computer programs which allow scientists to analyze and interpret the data. These programs perform all the necessary calculations to assign each pulse of sound emitted from the transducer a depth measurement or sounding. These soundings can represent the seafloor, a feature on or above the seafloor, or anything within the water column that may have blocked the sound from reaching the bottom. When all the soundings are put together, scientists can begin to see what the seafloor and associated environment looks like. Many times, with the use of high-resolution multi-beam data, the picture that is developed can even provide insight into habitat types, such as seagrass beds or reef structures. So why is this work important? Our oceans, rivers, lakes, and waterways make up a large portion of the Earth's surface, but only a small portion has been mapped with enough detail to be useful. Vessels of all sizes need to know the water depth of the areas where they're navigating so that they can travel safely from port to port. Fisheries industries and fisheries managers need to know where specific habitats are located which harbor certain species, and renewable energy sources such as offshore wind infrastructure need to ensure that they can establish systems safely and securely. Here at the USGS St. Petersburg Coastal and Marine Science Center, we are using bathymetry data to map changes in barrier islands and nearshore environments. This allows our scientists to better understand the seafloor and the associated environment, recognize changes, and provide predictions about how the seafloor, coastal environments, and coastal hazards may change in the future.
Okay, so I hope you understand what is bathymetry, why we are doing bathymetry and all. Okay, so what we have seen
Yes,
in the
yes, yes.
in that what is bathymetry, like why we are going for bathymetry first of all.
Mainly for locating depth of the seabed,
Yeah, then
then fish and other things.
then
It's like
understanding the
that.
sea floor also, we go for this bathymetry. Okay, and as you have seen, what we do, we use methods like echo sounding, then swathe bathymetry, and in swathe bathymetry, what you have seen, multiple beams are being given, and then we do the bathymetry for understanding the 3D imaging of seabed. Okay, so what I was writing here. So for understanding the water depth, then what kind of seabed is there, then the slope of the seabed and the location of interest. And if there are some features such as faults, ridges, etc., then because it will also give some obstacles in that, because which kind of thing we use the sonar to understand. Okay, so mainly what we use either echo sounding or the swathe bathymetry. In echo sounding, what we do in echo sounding, we see only one. In the video also you must have seen that we go for only single beam. In single beam we'll go for the locations that we are referring or we are interest. Then a sound pulse will be emitted. After that you must have seen that a sound pulse is emitted from the source, and which will travel down, and once it will reach the floor, ocean floor, or let us say if any obstacles is there, then it will reflect back and it will be received, or it will be detected by the receiver. Depending upon the arrival time, as we have done in the seismic reflection refraction survey also, depending upon the arrival time of the echo, the depth of water, for like we know the speed of the sound whichever we are transferring or we are emitting. So we know the speed of the sound, and we know the time how much it has taken. So based on that, the depth of water will be known. So let us say here the ship or vessel, whatever is there, and here we are emitting the sound. Okay, we are emitting the sound, and from here again it is getting reflected back, and let us say here the receiver is there, and it is getting detected in the receiver. Okay, now in the receiver, to go, let us say the depth is d, we don't know what is the depth. Okay, the speed of the sound wave we know. Okay, and the time that is taken to go and reflect back also we know. Okay, so the total depth is d, let us say, and again the sound wave will come back to the receiver. How much it will travel? D. So total distance that will be covered will be 2d. So we know speed equals to distance by time, so speed equals to how much distance it has traveled, 2d. Let us say t time has been traveled. So from this we can know the water depth. D is the water depth. Okay, so mostly the speed in the sea water, speed of sound in sea water will be in the range of 1450 to 1500 meter per second. Okay, and based on again, let us say based on the water quality or water whatever features are there for water, and this speed will change. Okay, so we have to consider, we have to keep in mind that what kind of water quality is there, what is the temperature of the water, if it is contained with some contaminant, or what how much amount of contaminant is there. So based on that also speed of sound will change. So we have to first see whatever water properties are there, and then we have to go for this, and then we can understand how much the depth of water is there. Okay, so what happens in this echo sounding is an active system will be there which will send out the sound pulse and will record its echo, and there is one passive system which will only detect the echo emitted by the objects as a result of the sound coming from the other sources. Okay, so if it is same thing is taking emitting the sound pulse and recording its echo, then it is active system, and if one passive system is there which will only detect the echo that will be coming from some objects as a result of like some because of the reflecting back of the sound waves from the other sources. If it is uh, detecting the echo, then it is called as passive system. And as we have seen, other than echo sounding, what we have seen, we can go for swathe bathymetry. So simple same kind of thing is there in echo sounding and the swathe bathymetry, but in the swathe bathymetry we see multiple beams are emitted covering a distance range of almost twice the depth of water, okay, from the sides of the vessel, and then the echo will be detected. Okay, okay, so let's move on to the question. And yes, frequency band to be used for the survey will depend on the water depth we are going to invest in. Okay, because see, this swathe bathymetry, as we have said, it will emit multiple sound beams. Okay, so this way the swathe bathymetry will give a continuous profiling of the seafloor, as we have seen in the video, and is very useful in case of surveying a larger area. Because if we are going for echo sounding, we have to go for several times, but if you are going for swathe bathymetry, in one go only you will cover a very larger area. So frequency band which will be used for the survey will depend on the water depth that we are investing in. So high frequencies like 100 to 45 kilohertz, that will be useful for the range of water depth range of 300-meter or so. Then come the medium frequencies. The medium frequencies like 30 to 100 kilohertz are useful in the water depths of up to 3600 meter. Okay, and low frequencies will be used for very deep oceans. So what is the question? So the question is, which frequency bands are useful for surveying very deep oceans? For very deep oceans,
So answer is C.
yeah,
C.
we
Low
have to go
frequency.
for low frequency bands. Okay. Next question is, what type of seabed will give a clear reflection in case of echo sounding offshore investigation? And your options are soft seabed, hard seabed, none of the above, and it does not depend on the hardness of the seabed.
Appears to be hard seabed.
Yeah,
B.
correct. Because if it is a hard seabed, it will give a clear reflection in case of echo sounding. So answer will be hard seabed. So next question is, in dash, multiple sound beams are emitted, okay, covering a distance range of almost twice the depth of water from both sides of the vessels, and echoes are detected. What will be the answer?
C.
C, swathe bathymetry, as we have seen just now. Next is, okay, there is one question. A submarine 100 meter under sea surface level used sonar to detect the ocean bottom. Okay, so sonar has been used to detect the ocean bottom, and 100 meter under the sea surface level a submarine is there. The speed at which the sound travels through the water is 1450 meter per second. The bottom of the sea is 2000 meter from the surface. Okay, calculate the time taken by the waves to reflect back to the surface of the sea. Can you please do this? Can you see how much you are getting?
2.69 seconds. 2.68.
Yeah, correct. 2.69. Okay. I'll do this because I'm recording this. People who will be seeing, I have to give for them also. No. So I'll solve this also. Okay. Wait. Okay, so what is there, that a submarine is there. Let us say this is a submarine, whatever I'm saying, submarine is there. Okay, and the under the sea surface level it is how much, 100 meter, and the surface of the bottom of the sea is 2000 meter from this submarine, or from the surface, oh sorry, from the surface. Okay, from the surface, this means up from here it is 2000 meter till the bed of the sea. Now what is the question? Sound is given as speed of the sound is given as 1450 meter per second. So how much sound has to travel? Sound has to travel total as 2000, the whole two times it has to travel. It has to travel like this, and then to get the sound to be detected from by the receiver, it have to come back. Okay, so as we have seen, it will be 2D. So 2 into 2000 it will travel, but see, this 100 meter is there below the sea level, so we have to deduct that. How much we are getting? 4000 minus 100, 3900 meter we are getting. Okay, velocity or the speed of the sound is given 1450 meter per second. So simply time will be how much? The distance by the speed. So as he said, it is around 2.69 seconds. So the correct answer will be 2.69 seconds. Okay. Okay, so let's move on to the next question. Next question is, a submarine 200 meter under the sea surface level sent sound waves to bottom of the sea and received an echo after 1.5 seconds. Consider the speed of the sound in the ocean as 1500 meter per second. Find out the depth of the seabed. Can you please do this? Options also I have given. Time of arrival is 1.5 seconds. Speed of the sound, let's say v, is given as 1500 meter per second, and 200 submarine is under 200 meter. Okay, as in the next last question also. Okay, you do this and then I will do it.
A.
1325. Okay. Okay, yeah, correct answer will be that only. Okay, see, so what is the question? Find out the depth of the seabed, or depth till the seabed, if I say. So what will be the total depth till the seabed? Anyway, 200 meter is under the sea surface. So 200 plus how much distance it is covering, right? So 1500 into 1.5 will be my velocity, right, distance, and the distance will be for both the after emitting and when it is getting reflected back. So it will be divided by 2. How much we are getting? 200 15 75 75 ही कहते थे 1205 2 11. So 1325 meter. Yeah, correct. So the correct answer will be 1325 meter. Okay. Okay, next question. So next question is, a vessel having source of sound at its bottom sends a sound wave towards the ocean floor and received an echo after 0.4 seconds. Okay, what will be the depth of water when distance between the source and the sea surface is 1.3 meter? Consider the speed of the sound in sea water as 1400 meter per second. Please do this. received an echo. So time of arrival is 0.4 seconds. What will be the depth of water when the distance between the source and the sea surface is 1.3 meter? Okay, speed of the sound is given as 1400 meter per second. What we need to find out? Depth of water we need to find out. So simply 1400 into 0.4, how much it will come? So the choke
B.
how much you are
281.
getting?
B
281.
281.3.
I think that is the correct answer. 560 meter you are getting. So 1.3 meter is given. So 560 by 2 plus 1.3 meter will be the total depth. 281, yeah, 281.3 meter, yeah, correct. So B will be the answer. Next question is, which of the following is not correct for echo sounding? Our options are: the depth is measured based on the arrival time of the echo. Next is sub-seabed profiling is generally done by echo sounding. Then the speed of sound pulse does not depend on the echo sounder, or none of the above. This sub-seabed profiling I have not discussed. This sub-seabed profiling means what? Let us say we several times what we do, we used some tow vehicle. So we use a tow vehicle that will be composed of source as well as the receiver. So in the towed vehicle there will be both the source and both the and the receiver. Now while the source will generate the seismic pulse, the receiver will detect the time of arrival of the seismic pulses as reflected or maybe refracted from different interfaces beneath seabed. Any other obstacles is there. Based on all that, so in towed vehicle what will be there? Both the this source and the receiver. So it will also generate and it will detect also the wave that is traveling back. So this there will be several like towed array kind of thing will be there. So towed array will be lying few meters, like here tow one is there, then like this there will be towed array. Okay, towed array will be at few meter interval below the sea surface, consisting of 2D receivers for high resolution survey, and most optimal frequency which provides the sufficient depth as well as the good quality data. It those kind of frequency should be adopted. So sources kind of boomer, then sparkers, air gun, etc. have a penetration depth range of 100 to 200 meter with low to good resolution. Then these vehicles, mostly we go for this in recent days we go for autonomous underwater vehicle. So this autonomous underwater vehicle, there should be that thing in here. Okay, let me see. Yeah, see this kind of thing is the autonomous underwater vehicle. So in the these stored vehicles are usually controlled by means of these cubes you can see that blue color, yellow color and black color, means of the umbilical cables that will be connecting inside. It will be there will be some cables that will be connecting to the main vessel. So there is one ship or the vessel is there. Okay, and from there there will be some cable that will be connected to these vehicles. These vehicles or this autonomous underwater vehicles will be consisting of performing the test for water depth determination, then seabed mapping, and then sub bottom profiling, then in situ measurement, and either storing the data or transferring to the main unit. All these things these vehicles will do. Okay, what was the question then? Okay, the question was, yeah, so question was, which of the following is not correct for echo sounding? Echo sounding, what we have done, echo sounding that one single pulse will send and then we'll calculate the depth and the seafloor. So what will be the answer for that?
This B.
B.
Sub-seabed
Because this
profiling.
sub-seabed profiling generally we do by which method? By using
AUV.
yeah, by
AUV.
using this type of towed vehicle. One of them is the autonomous underwater vehicle. Okay, so that's it for today, I guess. Yeah, any questions, any doubts till now?
Okay, thank you. Well presented.
Okay. Anyway, I don't know why people are not joining. Okay. Okay. Thank you so much.
Okay.
So we'll meet again next Monday for week 7 discussion. Thank you.
Okay.
Thank you so much.